So today I'm going to give you a brief introduction on how to balance the redox reaction. Before we get started, we need to first review a little bit of what is a redox reaction. So redox reaction is those type of chemical reaction where you have electron transfers being involved, and then the oxidation state of certain chemical species will be changed during the reaction. And then for a given redox reaction, what we can do is write them into two half reactions. That we have a reduction half reaction and an oxidation half reaction. What will happen for these two half reactions are that for the oxidation part, then you have the loss of the electrons being involved. And on the other hand, the reduction is where you have the gain of electrons being involved. And then that is typically we summarize for the oil rig, that you have the oxidation is the loss of the electrons, and then the reduction is the gain of the electrons. So in order for us to balance a redox reaction, we need to combine some of the previous knowledge that we have learned before, that to balance the chemical equations. So balancing the chemical equation we introduced in the earlier chapter, we emphasized that we have to balance the mass of each species, and then so that you can obey the law of conservation of mass. And then for a redox reaction, we need to do a little bit further because we also want to balance the number of electrons being involved in here. That being said, the electron lost by one of the chemical species has to be equal to the number of electrons gained by other chemical species. That being said, you cannot destroy or create the electrons during a redox reaction. To balance a redox reaction, we have to go through several steps, and then also depends on your environment difference. For example, whether it's acidic condition or a basic condition, the process will be a little bit different. For this given reaction right here, we're going to use that as an example, and then we're going to use this as the acidic conditions for you to understand what's going on in here. So given your redox reaction, the first step is you have to write it out in two half reactions. That being said, you need to identify the oxidation number for each species and then identify which goes through the reduction process, which goes through the oxidation process. So the iron 2 plus right here will give you a +2 in charge. The dichromic ion right here will give you a 6 plus charge for the chromium species. And then for the iron 3, you have a +3 in charge. Chromium on the product side, you have a 3 plus in charge as well. Based on the oxidation numbers identified, you can assign the oxidation half reaction and the reduction half reaction accordingly. The oxidation half reaction is where you have the electrons being lost, so that you have the iron 2 plus become iron 3 plus after the reaction because you lost one electron. And then on the other hand, for the reduction half reaction, you have the dichromic ion change into the chromium ion species. That your chromium change from +6 oxidation number to 3 plus oxidation number where you have gained 3 electrons. So the first step here, we need to try to balance the mass first for our redox reaction. The balance of the mass, you need to identify the same number of each species on each different site, except we're going to leave the oxygen or hydrogen, if involved, to the later stage. So to balance the mass, we take a look at the oxidation half reaction right here. You have one ion on the left-hand side and one ion on the product side, which is already balanced. And then if you take a look at the reduction half reaction, that you may notice you have 2 chromium on the reactant side, but only 1 chromium on the product side. So that being said, you need to add a 2 as the coefficient right here to balance the chromium species. Once it's balanced, we basically balance every single species except the oxygen in this case. So the next step, we need to try to balance the oxygen as well. So what we can do here in this case is to add water molecules that will introduce both hydrogen and oxygen in order to balance the oxygen. So what we can do is we're going to introduce some water molecules into this half reaction. And then what you will have, you want to have the same number of oxygen on both sides. You have 7 oxygen on the left-hand side, so you need to add 7 water molecules in this case in order for you to balance the oxygen. But once you're done with this step, you may notice although the oxygen is balanced, you also introduce the hydrogen species in here. So you need to do further reversion for the reduction half reaction here. So what you can do is you add the hydrogen species on the left-hand side as well in order to fully balance this half reaction. What you can do is you add the hydrogen ion species, and then you have 14, 7 times 2 hydrogen on the right-hand side, so you need to add 14 hydrogen ion on the left-hand side in order to balance it. And then the rest of the species, just copy it down. And then you will be able to get a fully balanced reduction half reaction. Until this step, your oxidation and the reduction half reactions are all fully balanced in terms of the mass. So next, what we're going to do is, in addition to the mass, we also want to balance the number of electrons being involved. So what we can do is to write out the number of electrons involved in each half reaction. For the oxidation part, you have the iron 2 plus become iron 3 plus. You lost 1 electron for that to happen. On the reduction side, what we can do is to count the total charge on each side and identify how many electrons are actually involved. If you take a look at the balanced half reaction right here, you will have plus 6 in charge on the product side. The water does not involve any charge in there. On the reactant side, you have plus 14 introduced by the hydrogen, and then you have a 2 minus introduced by the dibromine ion. So total, you have a plus 12 in charge on the reactant side. So in order for you to make these two charges identical to each other, you need to add in 6 electrons on the left-hand side to balance it. That being said, 6 electrons are actually involved in the reduction half reaction. So what you can do is to get this result and then copy it down to the organized part. So these are the number of electrons involved in each half reaction. And we also said for a redox reaction, the number of electrons lost has to be equal to the number of electrons gained. So what we have is we have 1 electron involved in the oxidation, and then we have 6 electrons involved in the reduction. So what we want to do is to balance the total number of electrons for both half reactions and then make the number of electrons involved identical to each other. What we can do is we times 6 for the oxidation half reaction, and then automatically introduce 6 electrons, which is the same number of electrons involved in the reduction half reaction. So if you write it out, you will have 6 iron 2 plus, produce your 6 iron 3 plus, and a loss of 6 electrons. So until this stage, you have 2 half reactions fully written out, same number of electrons involved, and then the mass already balanced. So the next step is also the final step, that you can copy down these 2 half reactions and then add them together. When you add them together, the electrons being gained from the reduction half reaction will be able to cancel out with the electrons lost for the oxidation half reaction. So the number of electrons that you balanced is crossed out. And then whatever left over will be the fully balanced redox reaction for the given problem. So this is the overall step for you to start with a given reaction and balance them accordingly based on the number of charge involved and also the number of species involved. You want to balance fully for both the mass and then the electrons for a given redox reaction.